Hello, chemists. This is Ms. Placino, and today in Skill Builder number 4, we're going to be doing just a quick review on graphing. So we'll start with some of the absolute basics about graphing, and then we'll talk a little bit more about how to use graphs to visually represent our data in chemistry. So let's dive right in. All right. So we know that any good graph is going to provide a visual representation of the data. And they say a picture is worth 1,000 words, so a graph is definitely worth at least 1,000 words in science. We tend to use scatter plots in ChemLab more often than not. Other classes might require the use of different plots, but this is the one that we're going to focus on for the time being. And typically, you want to provide a graph of your data when you are trying to either show that a trend exists in your data or when there's just simply a lot of numerical data to pick through. So if we take a look at the scatter plot that we've got to the right, with score on an exam versus hours spent studying, if we assume that each of those little blue diamonds represents a data point, you can imagine that looking at this just as like numerical values and not as a graph would be a little overwhelming. There'd just be a lot of numbers to sift through, and the relationship between the two variables might not be clear immediately. The second you take this data and you put it on a graph, it's really easy to see the trend, that the more time a student spends studying, more often than not, that corresponded to a higher score on the exam. So this graph in particular checks both boxes: too much numerical data to look at and a trend in the data that you want to show. When it comes to graphing, we're usually looking at the relationship between two variables, specifically our independent variable and our dependent variable. Traditionally, the independent variable is plotted on the x-axis. From time to time, you might see it on the y, but I don't really want to call it correct, but the traditional way of graphing is to show that the independent is on the x. And just as a reminder, this is the variable that you control or manipulate, or the one that you have a choice over during the experiment. On the y-axis, we typically plot our dependent variable, and that is the variable that is monitored or measured in response to the independent variable. So if we just look at another graph and kind of walk through some of the basics on graphing, we should always include labels and units for the x and y axes. The numbers themselves are, I don't want to say meaningless, but they don't really have a context. So this could be the relationship between any two variables. But once I start putting some of those labels and units on there, the information becomes a lot more meaningful. So in this case, I've got heart rate measured in beats per minute on my y-axis, and on the x-axis, I've got pace, minutes per mile. So in my head, I can start thinking, okay, this is looking at the relationship between how fast an individual is running and how their heart rate responds to those different paces. The scale on each axis should be reasonable. You don't want all of your data either to be squished into a little corner of the graph or not fitting on the graph. Since you will rarely, if ever, be graphing by hand at this point in your academic careers, usually your spreadsheet program is going to take care of this for you. You should also include a title. Generally, we're going to use y-axis versus x-axis as the title. Don't worry about getting creative, keep it simple and direct. So for this graph, it would be heart rate versus pace, y versus x. And finally, if you've got multiple sets of data on the same graph, you really should provide some sort of legend. So here I've got heart rate A and heart rate B. Perhaps that corresponds to two different test subjects, or maybe the same test subject before and after training. Surely there'd be more information in a lab reports. Okay. So let's take a look at an example. A student measures the volume of a liquid using a graduated cylinder. He then finds the mass of that liquid using an electronic balance. He collects data for a total of 5 samples and plots a graph. All right, so this is, of course, a very middle school level experiment. But let's take a little bit of time to look at how the graph would be plotted, make sure that we can label it correctly, and then find the relationship between the variables. All right, so let's assume that this is the graph that the student produced. What label and units should go on the x-axis, the y-axis, and provide an appropriate title for the graph. So based on the description of the experiment, see if you can figure that out. Pause the video and go ahead and write down your answers. All right, on the x-axis, we know that the independent variable is always placed there. If you look back at what the experiment describes, the student is measuring volume first and then measuring the mass. So they're seeing how mass changes in response to changing volume. That would lead volume to be on the x-axis. Volume in a graduated cylinder should be measured in milliliters. We know that mass is our independent variable, and it's probably safe to assume, since this is a science class, that the student is measuring mass in grams. As far as the title is concerned, we almost always present it as y versus x. So in this case, something like mass versus volume will do the job. So this was plotted using Excel or Sheets, I can't remember. But you can see that like the data takes up like the whole area, it's not squished. And we'll talk a little bit about the trend line and the equation of the line in just a few minutes. All right, what is the relationship between the variables? Well, hopefully as you look at this graph, you can see that as volume increases, so does mass. So I've got a direct relationship between mass and volume, and hopefully that's not particularly surprising. Question E asks you to circle the outlier. Now, there are statistical methods that you could use to determine if the data point in question truly is an outlier, but right now that's beyond the scope of this class. So maybe that's something that you'll do later in your chemistry careers, but not here. For finding outliers for our case, it's just going to be kind of visually looking at your data and seeing, okay, does everything kind of follow the trend or pattern that I'm expecting to see? So as we look at the 5 data points in our graph, it might be fairly obvious to you that data point number 3 is sticking off of the line quite a bit. The other 4 data points like all fall on that trend line, whereas this one is substantially below it. So I would identify that as the outlier simply because it is too far from the line. Okay, what does the slope of the line represent in this case? So we've got our formula of the line, and since it's a line, y equals mx plus b, m being the slope. So you've got a numerical value there. What does that represent in this case? So we know that slope is always rise over run, so change in y over change in x. And if we look at the units that we've got, we have mass divided by volume, which is going to be some measure of density. You might not always run into a case where like you have something that turns into a formula as you look at the slope. It's okay. All right, the last question I really want to look at is letter G. What is the mass of 9 milliliters of liquid? So when you were in middle school, when you did something like this, you probably would, trace over to 9 milliliters, then you'd measure up. Okay, it's about where it hits the line. Maybe you'd get fancy about it and use a ruler, and then kind of trace across to figure it out that way or roughly estimate it. We're really sophisticated and we don't have to use this rudimentary method of estimating what it would be. We can actually take the value and plug it into our equation of the line. So let's give that a shot. I'm going to erase some of this so that it's not so crowded on my screen. Okay. We know that y equals mx plus b, and in this case, y is our mass. That's going to be equal to the slope of the line times the volume, in this case 9 milliliters. Oops, ran out of room. Minus the y-intercept. So instead of estimating what the mass of this sample would be, I can actually calculate it and be far more precise than I would otherwise. So I'm just going to go ahead and plug this into a calculator. I would encourage you to do the same. And I'm coming up with, for the mass, when I just take it to all the digits provided to me by my calculator, I get 8.5498 grams. We worry about significant figures in chemistry, and the number of sig figs that show up in your formula of the line, I don't really know how a program like Google Sheets or Microsoft Excel calculates that from a sig fig perspective. So we're not going to worry about sig figs there. We're only going to worry about significant figures in our measured values. So in this case, that would be the 9.000 milliliters. Hopefully you recognize that that has 3 sig figs. So my answer should have 3 significant figures as well. So I would cut that down to 8.55 grams. And that's kind of it. You will definitely be using your equation of the line during lab 3 to find the concentration of your Gatorade or Powerade sample. Okay, I hope this little crash course on graphing was helpful, and you're able to put this into practice while typing up your labs. Thanks for tuning in.